Maybe we can get this started sooner or later here. Admit Philip. Okay. 2, 4, 7, 8 people. By the way, something we could do generally, like today in person here, we have 8 people, so there's 7 more people. If any of you are over in the dorms or something and want to come over, up to 7 more of you could do that if you wish to. The only problem is if 10 of you come, I have to turn some people away. But the point is, if you like to be in the classroom instead of at home, not home, but wherever you are, there is room today because some of the people who are able to be here are not electing to be here at the moment. So anyway, if anybody wants to show up and take a few minutes and run over here, that's fine. Not that anybody should ever consider running to my class. That's something they want to do, but sometimes. Let's see, admit. Okay, admitting more people. We're starting late today. I'm sorry about that. And Jordan, did you get, this is to Jordan right now, he's muted, but did you get the answer to your email?
Yeah, I believe I found somewhere I can go. Thank you, Dr. Brady.
So you're okay? You don't need any more help?
No, I'm good. Thank you.
Yeah, you're welcome. Okay. Okay, well, we have been talking about these notes. And I'm going to continue that and then kind of hopefully go to the book a little bit. But the book does, well, one thing I wanted to mention that's different. Philip Lindholm is joining twice. I don't know how that's going on, but we'll. So right now we have one person who is listed as trying to join twice. I've said admit them, but they're not getting through. If any of you know the reason I'm stopping here is because this one person was listed as joining twice, and now they're joining once, but they're not in yet. So I don't know. If anybody has chats with Philip Lindholm, you might chat with him and see what's going on, because I don't want him out in the waiting room the whole period. He probably, I don't know if you can you guys hear me in the waiting room?
I'll have it open, but no, we can't.
Okay, so I can't, there's nothing I can do. Okay, well, for those of you who can hear me, one thing in the book, everybody's able to join. I don't know what's happening. I think people are leaving and coming on the screen here. Okay, I'm going to try to finish the sentence. In the book, the author talks about curves that are smooth. In the notes, I talk about curves that are smooth and I talk about curves that are regular. The difference has to do with whether or not we are assuming the derivative function is continuous and not zero, or just continuous. Okay. I called in the notes something smooth if the derivative, if the function has a derivative that describes the curve and the derivative is continuous. For the author, he says, if in addition the derivative is not zero, then the curve is smooth. That's what I call regular. So I just want you to be aware of a distinction there between the two presentations. We will be dealing with regular curves from now on. The author deals with smooth curves, but that's the same thing. The smooth in the textbook means regular in the notes. I also have smooth in my notes, but that's different. Okay. Now, if you have gotten up to reading material that is from page 50 something on, 49, 50, actually 50 on, that's where we talk about the regular curves. I still see that Philip hasn't joined us. Anyway, the game is to define several functions from the original function. If we call the original function little g, then we call its derivative, first of all, g prime. But if we then divide that derivative by the norm of the derivative, we call that t for tangent vector. It's called a unit tangent vector. It's a tangent vector once you differentiate. As soon as you differentiate to g, you get g prime. That is a tangent vector. It will be perpendicular to the original. But if you multiply by 1 over its norm, then it becomes length 1 and it becomes a direction, and that's called a unit tangent vector. If you differentiate that function, you get what's called a normal vector. And if you multiply the normal vector by 1 over its length, you get the unit normal vector. If you cross product the tangent vector and the normal vector, you get what's called the binormal vector. Okay. Now, there's several things going on. It turns out that the binormal vector is automatically of length 1, so you don't have to divide it by its length. And the reason is that when you have a tangent vector and a normal vector, you may remember that the norm of such things, and there are other things here like t's and s's and stuff, and so these are not just vectors, these are functions. So to be more correct, I should put in where we're doing certain things. Anyway, this is the norm of the t vector, the norm of n. I hope you remember it has to do with the sine of the angle between them. But in this case, since t and n are orthogonal, the angle is 90 degrees, and so the sine is 1. And since the sine is 1, in this case, and also these are unit normal vectors, their length is 1, then the length of the binormal vector is automatically 1. So when you take a derivative of the tangent vector, it's not necessarily length 1. You have to multiply by 1 over its norm. When you take the derivative of that and you get the normal vector, it's not necessarily of length 1, and so on. So you have to divide it by its norm. But when you take the cross product of those two, you get something that is unit length. Now, last few days, we transferred things over to something called parameterization by arc length. If we do that, I called that capital G. So if we now have capital G and I differentiate it, it is automatically of unit length. okay? So that's different from the tangent vector, which you have to multiply by 1 over its norm to get the thing to be unit length. Now the capital G prime is therefore also a tangent vector, and it's also the unit tangent vector, and I use T to describe that also. So capital G prime is also T, except it's a different looking T because I want to distinguish between the normal vector, between the vectors in the space using the variable S with arc length and the original one using T. So I use kind of a squirrely looking T, or if you like a tau, like if you want to think of it as being Greek. Now, when I differentiate that T or capital G prime, I get capital G double prime. Okay, great. Now, the norm of capital G double prime is the curvature when you are dealing with arc length. One of the things we want to talk about in a minute is the curvature when you're dealing with the original parameterization. And the other thing I want to mention, and I want to go to the book, so if you guys have books somewhere in your home or wherever you are, or if you're here and you have your book around, if you don't have your book, I can pass this one around. But I want to try to show you why I go to all this trouble writing all these notes in a way. On page 904, okay, so let me do something here, and I hope it's readable. The author, instead of G, uses R. And so we can switch over to R if anybody likes. And so R is going to be a function of T. So we're going to have R as a big function of T. R prime is what the author is going to call, once you multiply it by 1 over its norm, this is what the author calls capital T. That's the unit tangent vector that I just talked about. Okay? Now, on page 504, that's not correct, 904, the author defines the curvature, and unfortunately he doesn't write of what, and he writes that that's equal to, I'm just trying to copy here, dt over ds. And he puts straight lines around it, which for me is double lines. Now, I'm hoping you guys at home can see this. If you can't, I hope you have your book available. In any event, how does the author introduce this idea of curvature? He introduces it as the norm of some kind of dt thing, which is fine. How did I introduce it? I used a capital G, so now I'm going to use a capital R, and my capital R is going to be a function of S, okay? And so I'm not going to go through the derivation right now, but what I used to call capital G is now capital R prime. What I used to call G prime is R prime. This is the unit tangent vector. This is what I would call T, with a strange looking T. I just said all this, except I said it with capital G instead of capital R. And if I would differentiate that, I would get R double prime, or T, strange looking T prime. And I define the curvature to be the norm of R double prime. So if you have the curve described as arc length representation, if you have it done that way, then the curvature is a function of S, and it is the second derivative of the original parameterization by arc length. Now, the author on page 504 introduces curvature. In fact, he's got a whole section by this. Now, curvature is not a constant. Curvature is a function. Okay? A function of what? It's a function of S, not a function of T. Okay? So if you have a parameterization which is not the one with respect to arc length, the curvature is not so simple as what you have when you do have a parameterization with respect to arc length. So what is it? The author says is this. So how do you work with that? First of all, when I say T is a function of S, then what's the variable? When I have in Calc 1, when I have y equals f of x, and I write dy dx for the derivative, what's the variable? X. So what's the variable here? S. But he doesn't write it because he hasn't developed this over here. He skipped the development of how you get to the curvature with S. And what did he do to do this? He said, and I'm over here a little further and maybe it's hard to see, so let me go back over here. I'm sorry for the way this is even worse than it was last semester when I was in class jumping around.
Money sheets let in.
I'm sorry?
Money sheets let in.
Well, Norman.
Money sheets let in.
Here.
Oh, thank you. Philip still wants in. I wonder why.
And then Keegan says he lost sound, but he
See
fixed
if Phyllis can get, Philip, can you come in? Something's wrong with Philip's machine. Or so.
Thank you, sir.
You're welcome. Amazing. Does anybody know Philip? Because Philip is now, he's trying to join twice. I'm now admitting him twice. I've admitted him 6 times now, but he doesn't admit.
He's not in our chat.
So I don't know what the problem is there's some problem, technical problem. So please keep reminding me if you guys see that. Can you see participants? Can you see the screen I have about people who haven't been admitted?
No, we can see who has been admitted.
Okay. Anyway, I'm sorry about Philip, don't know what to do. The author says, well, instead of T prime, if we use the other notation, that's dt by dt. Okay? And when we defined this stuff here, we said our circle S, this was, if you remember, we introduced a arc length thing to compose it, to get over to little r. I hope I'm saying that right. I'm worried about Philip. Still. Anyway, the point is that there is S prime of t. If S is S of t, then S prime of t would be ds by dt. So what I'm trying to get at here is I have, if I use notation with capital D with d's, S prime is ds dt and t prime is dt dt. What does the author do to get dt ds? He says, well, I'm just going to write, I'm just going to write things this way. And I'll get it said right in a minute. All right, this is what he's got. dt dt, that's t prime. ds dt, that's s prime. So what he does is he cancels a t and he gets dt ds. That's the author's way of introducing this subject. My problem is, how do you find the curvature? Because all he did was play games with symbols. He didn't define anything. I don't have a formula that I can, if somebody gives me a problem that says find the curvature, how do you do that? Okay, so what the author should do if he wanted to do it. He didn't, what they want to do here is have you learn stuff in terms of what they're trying to say without you having to see how it's done. Basically, in order to get to curvature, you've got to go over the standard representation, change things over to a function of S. And once you get the curvature in terms of S, you can then go backwards to find out what it is over in T. Okay? And so at the bottom of the same page, he has, and again, my problem is space here. He has the curvature of T, so he just calls that K, and that's a mistake because it's a function of S. But if you look at the bottom of the page, you'll see R prime cross R prime of T cross R double prime of T norm divided by norm cubed of R prime of T, or something like that. Now, basically, that's correct, but you need to learn it. So it turns out that what I would have done with K of S or something, I wouldn't do that. If I'm not going to do the stuff I tried to show you over there, I would just define the curvature using this formula. And then you could calculate stuff. Okay? Now, in WebAssign, there are several problems in section, I think it's, there was section 3 here in this page, where he asks you to find the curvature, where you're given a formula. In order to do that with the author, what you need to do is to take the original function, little r, differentiate it twice, do the cross product between r prime and r double prime, and divide by the cube of the norm. That's how you calculate it. All right? So he does that on page 904. At least he gets down to the bottom, okay, and he proves it over the next page over there. The proof, if you look at his proof on page 905 and you find the same thing in my notes, you'll find out we do the same stuff, except I don't play games with fractions d this and d that. Okay? What's involved is a function called the arc length function. And it's a composition that needs to come in. And so just to, again, to try to explain something, when you have things in the denominator like this, when I have r prime over norm of r prime, and somebody says, I want to differentiate t, the problem is what you have over here is a quotient. Okay? So, and I'll probably be saying this more than once. To get to the vector n function, the normal function, I differentiate t. When I look over here, that would look like a quotient rule. But the trouble is, I don't know how to differentiate a norm. So in this form, you can't differentiate the t because we don't know how to differentiate that. We actually do, but it's hidden. And if you don't introduce this function s, you won't know about this. So what am I saying? Well, I'll make it bigger here. We find out by talking about the integral of the norm of the derivative. This is the setup. This is what the function capital S is. I hope everybody can see it at home. Okay? And that's a one-to-one function. It has an inverse. The inverse is called S inverse, but the important point of it is that S inverse prime is 1 over the norm of R prime. So instead of writing this in a denominator, in order to deal with this kind of thing and differentiate again, what you do is you write this as S inverse prime of t times R prime of t. And now I have a product rule instead of a quotient rule. I have a function here. I know how to differentiate it. Okay? And that's the way you handle it. Now, the book is going to call this inverse dTds or something, because when you call a function dy dx is the derivative and you want to write the inverse, some people write dx dy. It's not so simple as just turning it over, because you remember you have to, for an inverse function, you have to evaluate it at a different place. But the author plays games with these symbols and makes his proof. For me, that's not good enough. I want to have functions that I can work with personally. So that's why the notes are longer than the book. The book does this in 1/2 of a page. It takes me several pages to do the same thing. But I wanted to mention that it's the key to everything. Everything that you do in here, when you look at my pages, yeah, I hope you do, and you look at some of these computations that are coming along in the mid-50s, or I should say in the mid-60s, you will see the capital S in various places coming in. For example, on page 60 in the notes, to show that this curvature that I've indicated here is correct, in the middle of page 60, I do some computations to develop that curvature formula that in order to do problems in WebAssign you need to use. Okay, and you'll see it takes about 1/2 a page to do because it's somewhat complicated. Okay, and you find out that cross products of things turns out to be the thing you need, because certain things are perpendicular, and so certain things drop out and so on. So I recommend you learning the proof, the proposition on page 60, which tells you how to develop the curvature formula for the original parameterization, because sometimes you don't want to take the trouble to go over to the standard representation. Why not? In order to do a standard representation, you need to integrate something. And this thing is the square root of sums of squares. I'm hoping what you remember, if you had to integrate the square root of sums of squares last year trying to find the length of a curve, those formulas sometimes were very difficult. So determining practically the arc length formula might be difficult, but there always is one. And therefore, what we do is we go theoretically into it. We don't worry about actually integrating this. And the reason is that we usually don't deal with the integral, we deal with the derivative. And the derivative of S here turns out to just be the inside. So the game here is you may not want to take the time or effort, or you may not be able to translate it into the arc length, but we do all the theoretical work in the arc length and then reproduce the formulas like on page 60 to get back to the regular parameterization. So once you've got all that developed, you wouldn't have to do the standard parameterization business. You could just use all the formulas that are developed, and that's what I put on the last page of your notes, which is a summary of all those formulas. Okay, so we'll be talking. Philip still wants to be admitted. Poor Philip. Philip, are you coming in? Yes, Philip. Philip is no audio. Philip, I hope you can hear me. We've been trying to let you in for a half hour. So I'm glad you finally reached it. I don't have your audio there, any audio for you, so I can't unmute you. I might be able to. Anyway, Philip is now showing us he's on, but only the video, which is, I'm taking time now, Philip, just because we've been trying so hard. The whole class has been praying that we can get you in here. I can ask you to unmute, but since you don't have the audio, it doesn't. If I really want to be mean, Philip, I have the ability to put you back in the waiting room.
You?
Yeah. Hey, thank you. Anyway, as I said, I don't know what maybe we can talk some other time. I don't know what the problem was, but you were showing us wanting to enter about 6 or 7 different times, sometimes twice at a time, and I had no way.
Weird.
It wouldn't work. So anyway, glad you're here. Look at if you want to look at the video of this later, you can see all the time we talked about you during the period. And so,
Yeah, I'm sorry about that. It was wonky on my side. It kept it said it was connecting, and then it would just close the app completely and
Yeah.
stuff like that.
well, you showed up as joining twice here most of the time, but the word joining was just dot, 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 like it's going to join. But anyway, so enough waste of time on trying to get you in the class. I'm glad you're there. We worried about you. Anyway, okay. So as far as these notes go, if you guys go to all the way to the end and look at the stuff where I sort of make the summary, and those pages between like 63 and 69 are trying to develop all these formulas. Some of this development is in the author's last section of the chapter 13, except what he does is he changes the names from T for tangent vector to V for velocity, because he's now going to call his original function R displacement. And when you differentiate displacement, you get velocity. So he gets rid of the capital T and changes it to V. And V is a vector function, but he also has the norm of V, which is a scalar number. So he uses B both heavy print and and regular font. Okay, and the second derivative, the n, is the acceleration in this context. So in section 4, he develops some of the same formulas you'll find on my page 69, but he does it with A and V instead of T and N and B. And so an old guy like me has a hard time translating. But if you'll look at the sections, the formulas I have on 69, and make the changeover to A and V, you'll find out that we are covering section 4 also, except I'm not talking about Newton's laws and stuff at the moment, but the formulas that he develops are all there. And so also in the exercises, examples in the book, the author has an example where he does all of these computations. He finds T and N and B. He has a problem about the osculating plane to develop the equation of those 3 different kinds of planes you get. You get one plane between T and N, you get another plane between N and B, and you get a third plane between T and B. And you can find equations of things of these planes. And there's a textbook example of this. There's also an example of finding the osculating plane, in this case for a parabola. There's a formula in case y equals f of x instead, in other words, the parameterization of a graph. And he does a parabola, y equals x squared, and he develops the osculating circle in the osculating plane for the parabola. Okay. Now, I'm saying all that because we spent so much time trying to get Philip into the classroom, I don't have time to show you those examples today. But in the textbook, there are examples of how you compute these things. Then, in section 13.3, which is now in WebAssign, is actually assigned, I think it's assigned for Wednesday or Thursday or something. There's a whole bunch of problems on solving, both finding just the curvature, finding the tangent, finding the normal, finding the binormal, and there's a bunch of problems like that. So what we might try to do Wednesday, it's difficult to do WebAssign when I'm in the classroom because I can put the WebAssign up on the screen, but unless you guys who come Wednesday all bring a computer, we can't talk about the problems, and therefore writing them down takes a lot of time. So if people would come Wednesday, try to bring some way to communicate, or not communicate, so you can see if we put WebAssign on the screen for the people at home. If you guys bring something, you'll be able to see it. So now we need to have a test. And so the test, I think, will be next Monday. Now, question, and this will be trying to get some feedback from you guys at home as well as you here. And let me just see what we have. We have 10 people on this on the web on the Zoom, and we've got 2, 4, 6, 8 of you. So we're missing one person, so one person is not going to hear this. I'm sorry about that. But we got Philip. So anyway, we could have a test. The test is going to have to be remote, not in class, because we can't get you all here on the same day. I don't like that because that opens up all kinds of cheating and other kind of possibilities. However, you guys are all honest. And since you're honest, we don't have to worry about cheating. I hope. Anyway, so if you're not going to cheat and you're going to take a test, would you rather have a test that's open book and open notes, or a test that's closed? Meaning you would certify that you took the test without looking at anything except your paper and thinking with your brain. Okay? No tutors and no calculators. By the way, no calculators for any of the tests I give you. That you can have open notes and open book and open everything else. You can look at WebAssign and all that. You can, if you vote that way. And you can look at the previous lectures if you want to, that are taped, but no calculator. The reason for no calculator is because it's possible to buy a calculator that will do all the problems for you. And so we don't want that to happen, because that just shows me that you bought a calculator. So anyway, we can have a closed test and closed notes, or an open one. Now, let me tell you the difference. Both of them rely on the fact that you're not cheating, but one of them will be that you're just sitting down for a period of time and taking a test like you'd be in class. And if you want to take a half an hour in the morning and half hour in the evening, the point would be that in the between, if it's a closed book test, you wouldn't be opening the book to see any more stuff that you forgot. In other words, you don't have to do it sequentially all at the same time, but you're not supposed to learn stuff in between, okay, if we have a closed thing. My idea would be to give you the test sometime this weekend, so you'd have the weekend to work on it and do like Monday night. So in case you don't want to work on it on the weekend, you could do it Monday night. Now, if it's a closed book test, I can ask you to define something. If it's an open book test, you can look it up, and therefore it doesn't make much sense for you just copying something out of the book. All right. So if it's an open book test, open notes and all that, you're going to get more problems to solve than if it's closed. Also, I might, if it's a closed book test, pick an example out of the text and give you an example, hoping that you read the text and solved the example already. If it's an open book test, I have to dream up a problem that's not in the book, okay? Because you can look at the problems to get help on how to solve problems, but I don't want you just copying the problem. So now, what do you guys think? Do you have any feeling about whether you'd like to have the open book or closed book test?
I think I'd rather have it closed, just because the definitions tend towards a better understanding if you actually know the definitions.
Okay, so we have one person in class today saying to give it closed, meaning relying on the fact that you guys are all honest, more honest than the other way. Anybody want to speak for open, sir?
I just have a question.
Yeah.
It'd be where you post test on Blackboard and then we print it off.
Yeah.
And then we re-upload it.
It would be that, yeah, it would be printed on Blackboard. You would download it, do the test, upload. So like the ones of you who were in my class last spring, that seemed to work.
Yeah.
And so then it takes a heck of a long time to grade, but that's the way that it's the nature of the beast. Yes, sir.
Speaking of the ones we did in the spring, did you get any satisfying data from us telling you where we got our information?
Oh, I don't know how satisfying it was, but yeah, I learned some stuff from what people said about, yeah. I can bring in those evaluations and show you, for example. because they don't have names, so, you know, I don't know who wrote what. And therefore, you guys, I think, could look at them and say, oh, look at that one, yeah. Anyway, keep out the proposals of money and stuff. Anybody, so do anybody disagree? Because we can vote, this is still America. We still vote. It's not a socialist country yet. Anyway. Anybody at home want to say anything?
We
Sure.
have like
Okay, go ahead.
we have like 4 people, 5 people, 6 people in the chat that say that they'd rather do open.
I think for the test, it's either got to be all open or all not open. I mean, if I understood what you said there. What I got to do for people talking is get back a ways because it's like overwhelming coming right out of here. Anyway,
Sir,
yeah,
I think open book test will be a good idea because we did the same thing back in March and April, and even though it was open book, we got more practice because the test contained problems from all the spectrum of those chapters, and means the problem were from WebAssign as well as from the text. So I think that would be a good idea to, I mean, in such a way we could get more practice of the problems. That's my say.
well, you're saying you'd like an open book test.
Yes, sir.
Okay. So we got both, which is fine. So are we going to put this to a vote? What do you think?
I think you can.
Okay. Now, I don't know how you guys vote at home in the sense that, I don't know, we can take some kind of nonsense we can do, but most of you are not showing me your faces and stuff, so I can't just say, raise your hand. I thought we had there's a reaction thing. So how do you, I guess you can react and we can see if I can, let me try to put everybody up. Okay, I've now got about all of you up on the screen, I guess. And so if you can indicate some way the way you wish to vote, in other words, what I'm saying is we'll give a vote here and either if I can see some of you and you could raise your hand, those of you I can't see maybe can do a thumbs up or something that I can see. I don't know how that's going to work yet. We'll see. Anyway, so the first proposal was to have it closed. So there's only 2 possibilities here. So if the majority of you say close, that's the way it'll be. If the majority don't say that, then it'll be the other way. Okay. So how many of you, first of all, does everybody understand that the nature of the 2 different choices? Anybody confused as to what I talked about? I tend to confuse people just naturally. Okay, then if you would like to have the thing be closed, in other words, just yourself, a pencil or pen and paper and your brain and no other help from other sources, indicate your preference. So I have 2, 3 in, this is for closed. Yeah. This is 4 inside here. And you guys at home, how do you? 5. 5 up here. What is the consensus? Is the consensus, anybody else want to add to that wants closed? I don't see any of you voting.
I mean,
I see Cameron put his hand up.
well, I mean, it's like, can you hear me?
Yes.
Okay. I was gonna agree with what I believe it was Keegan said in the chat. I can go either way, but
I don't have here, just a second, chat. Okay, chat, like what you did last semester. I just need a vote, not prefer open. I need to count. Keegan could go either way.
Yeah, I'm the same as Keegan. I can do either one, but I
Okay.
did enjoy what we did
We
last
need to have
semester.
10 people one way or the other. So we have 5 people inside. There are 5 more of you at home that want it closed. I see two said to go either way. We have one person who talked to wanted to keep it open. I'm sorry. Yeah, who wanted it open. Philip, you got a hand up. Is that to vote or did you just have your hand up?
No. Oh, I'm sorry.
Okay, I don't.
Do I just need to say open if I want it open and closed if I want it closed?
The idea right now is if you wish to have a closed test with no other stuff, you would be voting right now. And right now we have 5 plus 2 possible. So it appears for me that most of you want to keep it open. Awfully quiet at home. Okay, so, well, we've got a little bit of time. Why don't you guys think, I think we'll have to have an open book, open notes test, but we can do this again, maybe have a regular vote where you actually count on Wednesday. You don't want to waste any more time. Okay, so it's gotten to be 22 after. Sorry about things. I'm going to stop the recording here. And